We're going to look at the open short circuit test, brand new slide. Really excited to share it with everyone tonight. We're going to have a hands-on example. And what we're going to do is, so here's our primary referred circuit. Look, this is exactly how it appears in the handbook. Remember, what's missing here is your ideal transformer, right? N1, N2, and here is your actual V2. So anytime you see this circuit, remember that there's part of the transformer here that's missing. So what we're going to do is we're going to solve for our core values and our primary equivalent values using this test data. And that's going to help us be familiar with these values. So problem says, use the following test results from a single phase 120 volt, 240 volt transformer to complete the transformer equivalent circuit referred to primary if the voltage was applied to the low voltage side during both tests. Very important. Now, question, remember that part of the circuit I just drew? This is our voltage ratio, right? If I wanted to show the voltage ratio on this circuit, where would it go? If I was going to show 120 to 240, is it going to be 120 to 40? Is it going to look like that? No, right? It's going to be 120. Here's our transformer, right? To 240, right? N1 to N2. All right. It says voltage was applied to the low side. So we're going to say the low side is 120 volts. So in both the open circuit and the short circuit test, we're applying voltage to V1, the low 120 side. Remember, the problem has to tell you that. Okay, who can tell me? So here's my open circuit test. We're going to do open circuit test followed by the short circuit test. So open circuit test, what part of this circuit is missing? Our series winding impedance, right? Why is that? If there's no load on this transformer, remember from voltage regulation, what does this current equal when there's no load? 0. So we can neglect this series branch and we're left with just V1 across the parallel branch. See that? Now, instead of calling it V1, since this is the open circuit test, we're just going to call this VO for V open circuit. And instead of calling this, typically would be what? I1, we're going to call it IO for the current drawn during the open circuit test. All right, how much voltage do we apply during the open circuit test according to our test data? Maybe we're a field service engineer and we're testing a transformer and this is all, we applied this voltage and these are the readings the machine tells us. Yeah, 120 volts, great. So you apply 120 volts. How much current is drawn during the open circuit test? 0.15 amps, right? How much power is drawn? 4.2 watts, right? Now, this formula right here in the handbook, all this formula is real power in watts equals voltage magnitude times your current magnitude times what? In other words, if I multiply just V and I, what do I get? Do I get watts or do I get apparent power? If I just multiply V and I, do I get watts or apparent power? Ooh, careful, Deepika. Yeah, I get apparent power. So if I want to go from apparent power to real power in watts, what do I got to multiply this by? I got to multiply it by power factor or cosine theta, same thing, right? So in other words, this formula looks a little funny, but it's just solving for real power, and then you're solving for power factor. So let's go ahead and let's first solve for the power factor of our open circuit data. Let's change this to red. So step A, cosine theta O for our open circuit power factor is going to be equal to, what was our open circuit power from the test results? 4.2 watts. What's our applied voltage during the open circuit test? 120 volts. How much current was drawn during the open circuit test? 0.15 amps. What does everyone get for cosine theta 0 or your power factor? Let's see, 4.2. And there's a reason why I'm not taking the cosine of the inverse cosine just yet. Let's see, 4.2 divided by 120 times 0.15. Does everyone get, what was that, 0.233? Good job, Evan, John, Jillian, Addie, Daniel, great. So cosine theta is 0.233. All right, we're gonna leave that as is for now. Now, let's calculate IC. Okay, so here's B. What is IC? I've got two variables, R of my core and my magnetizing reactance. Sub C, right? This is the current drawn by just the resistance. So here is IC. All right, ready to calculate IC? IC is just how much amps were pulled during our open circuit test. 0.15, right? 0.15. What is cosine theta? Power factor, 0.233, right? I'm rounding, of course. All right, what do you guys get for IC? How do we do this in our calculator? I'm just going to do times. There's all my decimals, so I'm accurate. 0.15. Great. I of C is 0.035. All right, ready to calculate R of C. What's the next step? What formula is this? What formula is this? This is just, yeah, Ohm's law. Good job, everybody. Yeah, this is just Ohm's law. That's all it is. Do I know VO? Sure do. 120 volts applied. Do I know I of C? I just calculated it. Can I determine R of C? Sure. 120 volts over the same 0.035 amps. Tell me, what do you guys get for R of C? And I'm just going to bring this guy, bring it right back here. So in my calculator, I'm going to do 120 divide by second answer. Big number, right? What is that? I'm going to say 3.43 kilo ohms. Your core impedances, or I should say your core reactance and resistance, are usually going to be quite high. So don't be scared by these big numbers. Let's see. Good job. Stefan, Meg, Addie, Paul, Suman, Selmont. Oh, yep. Great. Thaisa, great. All right. We just calculated R of C, right? R of C equals 3.43 kilo ohms. All right. Next step. And I meant to do this first. Where do these formulas come from? So if this is I of C and this is I of M, the next one we're going to solve for, right? The current drawn by the magnetizing reactance. Where do these formulas come from? So it would be KCL if we knew the different angles, right? But we don't know the angles yet. How about this? Look at this phasor diagram. Here's complex I of O. Here's magnitude I of O. Here's the real component of I of O, right? And then this right here is going to be the imaginary component of I of O. How do I solve for the real component of I of O? Right? It's going to be magnitude IO times what? Times cosine theta O. Oops, sorry about that. And look, what does that equal? There's I of C. So we're really solving, these are just magnitudes. See that? How do I solve for the imaginary component of I of O? I'm going to multiply the magnitude of I of O by what? Is it going to be cosine theta or is it going to be sine theta? In this case, we're calling it theta O. And here is IM. All we're doing is we're converting complex IO into its real and imaginary component. That's all these formulas are. And why can we do that? Your resistance, so this is a voltage divider. I'm sorry, excuse me. This is a current divider. Let me clarify. This is a current divider, right? Anything in parallel splits up the current. Your resistance is the real component of impedance. Your reactance is your imaginary component of impedance. So if this is a complex current, right? We only know the magnitude right now. The current through the real component of the impedance is going to be the real component of this current. And that's going to be the imaginary component. Pretty neat, huh? All right, I of M. We left this as cosine theta O, so we can plug it in right here. But now we're going to solve for theta, right? So let's call this step C. So first, let's figure out theta. I'm going to zoom in because I'm getting a little messy here. How do I solve for theta O? How about the inverse cosine? Yeah, you got it, Gene. Inverse cosine of that power factor of 0.233, right? In other words, I'm just one more step. I'm just solving for theta O. What do you guys get for theta O? I want to be accurate, so I'm going to do inverse cosine. I'm going to scroll up until I see all of those decimals. 0.2333, that's our power factor. Pull it down. What is that? 76.5 degrees. Great. So theta O is 76.5 degrees. Good job. You again, Paul, Salmont, John. All right, let's solve for I of M. Ready? I of M equals, what's IO? The same, 0.15. Hasn't changed. And let's put amps right here too. Always try to include your units when you can. Keeps you out of trouble. All right, times sine of 76.5 degrees. So in my calculator, I'm going to say 0.15 times sine. Oh, not pi. There we go. And I'm going to do second answer. Everyone getting the hang of using second answer in their calculator or scrolling up and bringing values back down? You want to speed up how quickly. That's the only tool you got in the exam room. You want to speed up how quickly you can use it. All right, everyone get, what is that? 0. We'll call that maybe 15, or we'll say 146. Good job, Michael. Saeed, Jillian, great. Thaisa, great. John, excellent. So remember, these are just magnitudes. These are just magnitudes. So you can have, when these are all complex numbers, they're going to split into this voltage divider. So we're just looking at the magnitude. Remember, your complex numbers, if you just look at the magnitudes, you can't really compare them. In other words, IM is almost equal to IO, just about. But we're not adding plain numbers, we're adding complex numbers. All right, last one, X of M, ready? What formula is this again in the chat? This is just plain old Ohm's law, right? All right, let's solve for X of M equals, look at this. I know the voltage across X of M is VO. I know the current through X of M, that's IM we just solved for. So that means I can solve for the impedance from here to here, which in this case, it's just going to be a reactance. So 120 volts divided by 0.146 amps. Bring this guy back down. In my calculator, I'm going to do 120 divided by second answer. Uh-oh, went a little too fast there on my keyboard. Let's get out of here. And we'll do, did it again. One more time. There we go. 120 divided by second answer. Let's see, about 822.7 ohms. Is that what you guys get? Awesome. Good job, Harish. Addy, great. Michael Chow, great. Excellent. All right. You want to know a quick way to check this? What's my angle for C, IC? What angle is this if it's a real component? 0. What's my angle for I of M? What's my angle here? 90. Let's add them up. Remember the complex numbers. 0.035. I'm just going to do the rounded decimals. We're going to leave that. Oh, try again. 0.035. It's lagging. Yep, thank you. 0.035. I'll fix that in a second. Minus, where's I of M? There we go. 0.146. And we're going to do, actually, that needs to be, we need to add this. I'm sorry. Current entering equals current leaving. Both of these are leaving. And then here's going to be minus 90. And then I'll fix minus 90 here in the notes. And then we'll talk about why it's minus 90. That should get us to 0.15. And what was our angle? 76.5. How about that? Looks good, right? Works out. This was minus. Why was I of M negative? Really, I should have drawn this upside down. So this is R of C, and this is minus JX of M. Plus J X of M. Okay. All right. So what was X of M? 822.7 ohms. 822.7 ohms. All right. That's the open circuit test. Question. If I know R of C and I know JX of M, can I solve for P of O? Sure can. What formula would I use? Is this parallel or series? Yeah, V squared over R. You got it, Randall. Let's check. Ready? Let's say PO equals V squared over R. If I'm solving for PO, this is VO and this is RC. Why am I ignoring X of M in this calculation? Why am I ignoring X of M? I only know my watts, right? Yeah, no bars in PO. All right, what do you guys get? 120 volts squared divided by that really big 3.43 kilo ohms, 3.43 kilo ohms. We'll just use the decimal values. So it'll be a little rounded, but it should be pretty close to 4.2. Divided by 3.43 e to the 3. Ta-da, 4.2 watts. So that's that same V squared over R formula we looked at, that we talked about in the Power Boot Camp, and then we talked about at the beginning of circuit analysis class. All right, that's the open circuit test. We solve R of C and X of M. You guys ready to solve for REQ and XEQ of the short circuit test? Short circuit test. I'm going to apply a short circuit on my secondary side of my transformer. What happens when I short that secondary terminal? What happens when I short circuit? How big is this current right here? So here's, what is this? I2 over A. It's huge, right? It's going to be big. I2 over A, when we short that out, is going to be much bigger than what? IO, right? Now, looking at a regular circuit, IO would equal 0 if we short it, but we still have a little bit of impedance here. So you're going to have a small amount of IO, right? Because we're not shorting directly around IO, right? We still have this impedance. So you're going to have a little bit of IO, but I2 over A is going to be so much bigger than IO that we can essentially say IO is approximately equal to 0. So if IO is approximately equal to 0, what part of the circuit do we get to neglect during the short circuit test? And if you're not sure, look at our short circuit test circuit. What's missing? Yeah, we say goodbye to the core, and we're only going to model our series winding impedance. And instead of calling this V1, it's the short circuit test. So we're going to call it V short circuit. And instead of calling this I2 over A, we're going to call it I short circuit, because this is the current drawn during the short circuit test when we apply a specific voltage. You usually, why do you apply typically a really small voltage amount when you do the short circuit test? Or how about this? What would happen if you applied normal voltage during the short circuit test? Would you want to stand next to that transformer? No way. Yeah, you cook, right? You let the magic smoke out. So you only put a little bit of voltage. All right. Let's solve for REQ over here. So step A. What formula is this? R equals P over I squared. Look, this is just P equals I squared times R. Remember that? If I use I short circuit, why can I solve just for R? Why am I ignoring my X when I use, when I divide my current into my power? Why am I ignoring X and just solving for R? Yeah, because what's my units for power? It's just watts. So let's see over here at short circuit test, how much voltage do we apply during the short circuit test? So we short the secondary of the terminals. We slowly ramp up the voltage. In this case, we're going to apply 16.2 volts. And the measured amount of current drawn at that time is 9.1 amps. And during that time, the transformer is drawing 41.3 watts. Is the transformer also consuming some reactive power, some VARs? Is it also going to consume some VARs? Yeah, sure is. How do we know? We got an inductor right here. However, we're really only concerned with right now is the watts, and we'll see why. So go ahead. What do you get for REQ? Let's see. Short circuit power was 41.3 watts. 41.3 watts. Be really careful. The biggest way to get these equations wrong is you forget to square them. A lot of times on my own notes, I'll even circle that square because sometimes I get in the habit of writing it too small and I miss it. So I enter the numbers wrong. All right, my calculator, 41.3 divided by I squared, 9.1 squared. Looks like, does everyone get 0.499 ohms, right? We could even what? Even just say 0.5 ohms if we want to round a little bit. All right, looking in the chat. Good job, Alan E. with an E. Randall, Heather, Talon, John, great. Saeed, great. Gene, Suman, Daniel, great. All right, we solved for REQ, right? We'll say 0.5 ohms, right? This guy right here is 0.5 ohms. How the heck do I get XEQ? What formula is this? We'll call this step B. What formula is this right here? Ohm's law, right? V equals to I times Z, solved for Z. I know my voltage, I know my current. These are only magnitudes. So here's how it looks in the handbook, but remember, these are magnitudes. So if I divide just the magnitudes, what value am I going to get? Am I going to get complex Z, magnitude Z? Am I going to get R? Am I going to get X? If I just divide my voltage magnitude, my current magnitude, I'm going to get my impedance magnitude. So what do I almost wrote 120. What do we get for the impedance magnitude? Let's see, 16.2 volts divided by 9.1 amps. What do you guys get for ZEQ? Let's see, in my calculator, 16.2 volts divided by 9.1 amps. Does everyone get, what is that? We'll say 1.78 ohms, 1.78 ohms. Excellent. Stuart, you got it. Great. Jillian, great. Mubashir, great. Alan with an A, great. Or Alan A, excellent. Michael, excellent. All right, question. I know R, I know magnitude Z. Can I solve for X? What formula is this? What formula is that? Pythagorean theorem. Yeah, you got it. Look, if this is complex Z, this is magnitude Z, this is R, my real component, this is X, my imaginary component. This formula is just magnitude Z squared equals R squared plus X squared. That's all it is, Pythagorean theorem. So step C, solve for the total reactance referred to the primary. XEQ equals, we'll say 1.78 ohms minus REQ 0.5 ohms, and then all under the square root. Oh, see, I told you I miss those squares sometimes. All right, what do you guys get for XEQ? I'm going to do didn't like that. Let's try that again. There we go. I'm going to do second answer squared. There's my 1.7 ohms minus, I'm going to scroll up, look for my 0.5 rounded. Here it is. I'm going to square it. I'm going to hit enter. And then I'm going to do square root second answer. I'm going to do that in 2 steps. All right, everyone get, what is that? We'll say 1.71 ohms, something like that. 1.71 ohms, 1.7 ohms, however you want to round. Good job, Ian, Mernouche, Tyler, Daniel, Scott, Sam, Michael, Heather, Jacob. Fantastic. So we just solved for the final parameter, 1.71 ohms. 1.71 ohms. All right. Last question on this page, and I forget your name, I'm sorry, but the person that asked for, what exactly is percent Z? So percent Z, it comes from the manufacturer. When they build a transformer, it's one of the last steps they do before they make that nameplate and slap the nameplate on it. So who can tell me, how do you calculate transformer nameplate, percent impedance? Careful, not in the handbook. Let's see. Robbie said voltage short circuit divided by nominal primary voltage, where I short circuit is I rated. Beautiful. So look, percent Z. And this is actually how they calculate it at the manufacturer. They do a short circuit test. Short circuit test is primarily used to calculate percent Z, but it also helps to calculate the parameters. But for the most part in power engineering, you only care about percent Z because that's what you use in fault current calculations, right? So percent Z is going to be V short circuit divided by V rated. But it's not just any V short circuit. It's got to be the applied voltage during your short circuit test when I short circuit equals I rated. In other words, V short circuit when I short circuit equals I rated. In other words, you apply a voltage, you take that dial and you slowly crank it up, right? Your voltage, and you stop as soon as your amp meter measures the rated current on that leg. You stop. Whatever that voltage is, you divide it by the rated voltage on that side. That's how you calculate your percent impedance. Now, question. Can we calculate the percent impedance of this transformer? Yes or no? From what we know on this page. Can we calculate the percent impedance? Yes or no? Those of you that say yes, why do you say yes? And those of you that say no, why do you say no? We have V short circuit. Careful, Brian. Remember, percent impedance, it's not, I can apply, during the short circuit test, I can apply any voltage I want, and I can use that current and the measured power to calculate REQ and JXEQ, because they're all going to be proportional. The current that I measure and the power that I measure, it's going to be proportional to the voltage with respect to these formulas. But if I want to know percent Z, number one, I need to know what's the rated current on that side. So if we're doing the short circuit test, if I'm measuring the current either on the primary or the secondary, right, I need to know the rated current. I could solve for it if I knew the apparent power rating, because I have the primary voltage and secondary voltage. So how about if I say this transformer is 75 kVA, can I calculate percent Z now? I can. What's V short circuit? Idaho Joe says no. Aaron says no. Aaron and Idaho Joe, what do you guys say now? What else are we missing? If this was a 75 kVA transformer and this is the low side, right? If voltage was applied to low side, what's my rated current? What's my rated current? It would be 75 e to the 3, right? Divided by 120. My rated current on the primary is 625 amps. Is I short circuit 625 amps? No. I short circuit is 9.1 amps when the applied short circuit voltage is 16.2 volts. In other words, I would have to I would slowly, ever so carefully increase this in very small increments until I short circuit is equal to that rated current. As soon as I get that rated current, then I stop. And that's the value that I divide, in this case, by 120, by the rated voltage. So careful. You divide the short circuit voltage when your short circuit current, when you reach your rated current, you divide that by the rated voltage. Make sense? All right, I'm just gonna peek down below. All right, any questions on open and short circuit tests before we look at the three-phase delta connection? It's about 8:14. I'm hoping to keep it right under 3 hours. We'll probably go about another 30 minutes. It'll be about the same duration as that last night I'm planning. Those of you, if you're stuck here, did you watch the videos in the on-demand course? Because I know we go in much more detail on that. So if you haven't worked through the on-demand course for transformers, if you haven't done the pre-work, that's where I strongly suggest you reference and you do the pre-work to better understand this. Taylor said, yes, the review court is great on that. Yeah. And I know not everyone has time to go through their pre-work, but it's really important. Typically in live class, we're going to go over as much hands-on examples as possible so we can teach by doing while I point out all the things to watch out for. But the content of the exam is so big. It's really important to make sure, at the very least, work through the videos and work through the quizzes. David said, can the short circuit test be done on either side? Yes, it does. You can. The short circuit current can ramp up quickly. So a lot of times you'll short the high a lot of times the high voltage terminal is shorted because the high voltage terminal is the low current side. So you'll have less amps when you short it running through that short circuit, but it doesn't matter. You can do it on either side. Alan said live class explanations are so much better. Yeah, they're a lot better. They're so much more fun. They're more interactive. It's easier to pay attention. I totally agree. All right. Marvin said, why is I rated not 750 kVA divided by 240? So we applied voltage to the low voltage side. So I'm assuming that we're measuring our amperage right here. In other words, this is I short circuit. So really we have what? Really, we've got our ideal transformer, right? That's going to look like this. So really, we've got this. Uh-oh, don't like that. There we go. And here's our short, right? But we're measuring the short all the way over here is what we're assuming. Yeah, Tyler, you got to memorize this because this is not in the handbook as of right now. With a little practice, though, it's not too bad. All right, any last minute questions before we talk about three-phase? We're going to draw a delta Y connection together. Then we're going to do a fun example with single phase versus three-phase voltage ratios for a three-phase transformer. Then we'll do open delta and high leg delta.